Coming back to the model construct screen, what we can do is we can produce the best model we can and then save it as a benchmark and then continue modeling, trying to beat the benchmark. To back up a model, just click the Active to Backup button. This then saves the active model as a backup. The green line is the backup model and the blue line is the active model. In this case, the green and the blue line overlap because we've just saved active to backup. You can continue modeling, trying to beat your benchmark, and the blue line along with the orange line will change. The green line, reflecting the backup model, won't change until you save the active to backup again. Let's just remove importance of faith and add a few, and remove effects of legal gambling. Add a couple of other things to the model, other variables to the model. Click refit and then just see how that changes highest level attended. So here, the green line hasn't changed. This is the backup model that we saved a second ago. But because Preddle models all the predictive variables at once that we've ticked, the blue line, or the active line, for highest grade attended has shifted around in order to compensate for other variables that have just been added. You can add more predictors to the model, as we just did, or take predictors out, effectively trying to beat your benchmark. Your benchmark being the backup model that we saved a second ago. If you decide that you can't actually beat your benchmark, then you can always copy the backup back over the active by clicking the backup to active button up here. So, having saved your backup in this way, and having tried to beat your benchmark, how will you know which model to prefer, active or backup, beyond eyeballing the lines across the various predictive variables? How can you evaluate? Just click Model Compare in the GLM menu to bring up this screen. Model Compare provides diagnostics for the active model and backup model side by side. It summarizes the settings that you chose: log link function, dataset num records, workspace num records, and so on. One thing to note is that the dataset num records is the number of records in the file that you uploaded, whereas workspace num records are the number of records in a workspace for which the weight is greater than 0 and the transformed offset is a valid number. 2,947 records were in the original dataset, but about 80 of those had 0 weight, bringing the workspace num records to about 80 less than dataset num records. Now, the total sum of squares is the sum across all records of the response minus the average response all squared. It's effectively the total variation in the response variable. The regression sum of squares is the amount of this variation that is explained by the model, and the residual sum of squares is the amount of variation remaining unexplained. The R-square is the regression sum of squares divided by total sum of squares. It's effectively the percentage of variation that's explained by the model. However, the R-square and the sum of squares values are really only relevant for normal linear regression, i.e. with an identity link function and normal area distribution. For other model types, such as with a log link and a Poisson area distribution, these statistics here are much less relevant and can be misleading if relied upon. When looking at GLMs, the deviance is a much more useful measure of model fit. The lower the deviance, the better the model fit. Now, you can reduce the deviance by simply overfitting the model, adding in plenty of predictors with plenty of parameters, not grouping, not trying to simplify the model in any way. As a result, the model will fit to noise in the data that you've got there. But that isn't a good model, since it is fitting to noise, rather than trying to produce a model that generalizes to other data. What you want to do is get a good compromise between a model that fits well to the data, i.e. has low deviance, and is still a simple model with a low number of parameters. Notice the number of parameters here is 24 versus 16. The AIC and BIC metrics here combine these trade-offs to give a balanced view of model goodness. Now, the AIC is equal to the deviance plus 2 times the number of parameters in the model. For example, in the active model, this AIC of 2,837.37 is literally equal to the deviance plus 2 times the number of parameters of 24. And the BIC is calculated a similar way. It's equal to the deviance plus the number of predictors times the log of the number of predictors, i.e. this BIC 2980.43 is equal to 2789.37 plus 24 times the log of 24. The BIC measure penalises the number of parameters more strongly than the AIC does, but the AIC has more theoretical support than the BIC. They're essentially measuring the same thing and are calculated in a very similar way, and different users have different preferences for either the AIC or the BIC, and both are commonly used in practice. If you choose a model with a low AIC or BIC, then you're on the right path to hitting a good compromise between a well-fitting model and one that isn't over-parameterized. In this case, comparing the active model and the backup model, the active model has a lower AIC but a higher BIC. So depending on which measure you find to be more relevant, you may prefer the active model or you may prefer the backup model. In both metrics, the objective is to choose the model that has the lower AIC or lower BIC.